Welcome, all my Computer Foundation students. I know I already have a video out there with a lot of 112 already explained, and several of you have already turned it in because you got on it and did it last week. But this week we're going to have 112 and 113 due. So I thought I'd recap 112 in case some of you can't find the video. Just a quick recap. It was recording number 4. This is recording number 5. So we're going to do a little recap on this one, and I will save this video and upload it in the calendar and on the assignment. And then I'll do another video on 113 and explain what that is and what that entails. Again, just to explain, I am in Project Lead the Way. If you're in Project Lead the Way and you click on 112, it will tell you everything you need to do. We're going through the 112 curriculum. Now, if it has you create something, you will save that and you will upload that to Canvas. Also, all the questions and all the things it asks you to do, you will do that and save it on a Word document, and that you also will submit to Canvas as evidence that you did the work, and then I can give you your points. If you are behind and you need help getting on Project Lead the Way, because you need to see this, not see mine on the video, you need to be able to get in on Project Lead the Way because there's more than what I go over. I just skim through it. So you need to have it, and a couple of you don't have that yet. So please get with me so that we can get you on Project Lead the Way. Okay, enough said. Activity 112, how a computer works. We're going to learn about data represented by using bits and bytes. We're going to learn how to use bits and bytes and how that's transmitted across wireless connections so that we can contact people not just in our neighborhood or not just Indiana, not just the United States, but all over the world. Anybody that has Wi-Fi, if we're using Wi-Fi on this end and we send it to them, technically they can get it as well. So it goes through and it talks about the different operating systems, talks about hardware, operating systems, and applications. You need to know that information because that is something that will be on the final exam. So please take the time to read through this and make sure that you understand what things are. I'm going to quickly go on to data representation. Have you ever wondered how data is stored on an electronic device? Yes. How pictures can be saved on a phone or music can be played on a mobile device, how images, sound, video, other forms of data, they're all translated in the digital world. So it looks at electronic devices, electronic components. Can you guess what a deci means? Well, it's 10. So we have considered to be T. When it's binary, it's always either on or off, or in binary code, it has to be a 1 or a 0. So read through this because they do a really good job of explaining if it's off, it's 0. If it's on, it's 1. And then it says if you have 2 bits together, it should be 2 times 2, which equals 4, or 2 squared. So then they show the possible combinations. You could have 0, 0. You could have nothing and 1, which would be 0, 1. You could have 1, 1, which would be resulting binary numbers 1, 0. Or you could have nothing and 0, which should also be 1, 1. So those are 4 different combinations of what it could be with 2 bytes or 2 bits. Can you guess how many values you can store with 3 bits? Well, now it's bigger. You have 8 values of how it can be stored and how it can be mixed up. Computers use a combination of bits, allowing for more values to be stored. This is really good information. This is how we get 256 values. When we do RGB, red, green, blue, the colors, it's 255. That's why it handles it when it's 256 bytes of information. Okay, so read through that. Now we're actually getting to some nitty gritty. Humans use the decimal numeric system or base 10 system to represent numbers. So let's look at the number 4629. 4 is in the thousands place, 6 is in the hundreds, 2 is in the tens, and 9 is in the ones. So the number 4629 is 4 times 1,000, 6 times 100, 2 times 10, and 9 times 1. These place values can easily be converted to powers of 10. And they explain all how that works. So their digit places, if it's millions, it has 1, 2, 3, 4, 5, 6 zeros behind it, right? If it's 100,000, it only has 5. If it's 10,000, it only has 4. If it's 1,000, it only has 3 zeros behind it. 100, 2, 10s, 1, and then ones has no zero behind it, okay? All that's good. We're just learning how the place values work. In the binary number system, this is really important. It's 1, and then 2's is 2, 4's is 4, 8's is 8. So you go 1, 2, 4, 8, 16, 32, 64, 128. I put that, if I have to convert between binary and digital and then digital to binary, if I have to go back and forth, I do this chart right here. I don't do the 2 to the 7th, 2 to the 6th. I do the 1, 2, 4, 8, 16, 32, 64, and 128. And I'll tell you why. Because when we're converting, the next step, if you have a number like 22 and they say, what does that really equal in digital code? They're going to put it at 10110. And okay, if we know it's 1, 2, 4, 8, 16, 32, 64, 128, I can go back on those places. There's nothing in the ones. There's a 10. This isn't a good way to explain it. Well, it is. You got a 1, a 4, an 8, and a 32. So you've got 44, 45 is actually what it equals in digital, because it goes back and forth and they do it to the whatever power, but it's really 1, 2, 4, 8, 16, 32. The next highest is 64, and we know 45 is bigger than, or is smaller than 64, so we can stop at 32. We know there's going to be 132, and if you take 45 minus 32, then you know we can also squeeze an 8 in there, we can squeeze a 4 in there, and we can squeeze a 1. Now I'm going to show you how practice binary to decimal conversion. I don't like how they did it this way, but if you have 110 and 11, it's actually going to be 5, because it's going to be, no, 1 and 2. You're going to have the 2 place. That's not right. Okay. Okay. Bad way to do it. Okay. Let's see if I can get a better way. These are what I'm talking about. So if we've got binary of 0, 0, 1, 0, 0, 1, 0, 1, I can translate that to a decimal. I know there's no 1, there's no 2, there's a 4, no 8, no 16, there's a 32. So it's going to be 32 plus 4, so it's going to be 36 in decimal. Guess they don't have any to check your answers. But in your Word document, you'll want to answer all these questions along the way so that you can have it go back and forth, okay? So that you can tell it what its worth is. Now, we're going to get into this ASCII because I want to make sure that you understand this. ASCII is like how we do colors, okay? And it says ASCII originally used 7 bits to represent 128 unique characters, but was later extended to 8 bits so that it would have 256. Now, we know RGB is 255, 255, 255, which in essence, well, you'll see the table here. Maybe, if I can get it to load. Sorry, my internet's poop. Okay. Well, in the ASCII table, they're representing letters for numbers. So if you use the number 123, it would be a left bracket. So they do that based on numbers instead of just characters. And you can do that back and forth, but it's kind of like a secret table to do some unique conversions. So you can always flip over there and check that out. But it says in real life ASCII code of a character, they use decimal numbers. For example, ASCII code 65 stands for the capital letter A. So it wants you to use the ASCII table here, and also whatever the decimal number is, also look up what is the character. So that's how we were going back and forth on that. There's also Unicode. Although ASCII is one of the original standards developed for character encoding, it's not the most common standard used today. The most common is called Unicode. It's a multi-byte character encoding that covers most of the world's languages and writing systems. Because, you know, there's a lot of different languages other than just English. So, and it talks a little bit about context matters. It talks a little bit about abstraction. Please read all of that. And then add to your notebook, data abstraction provides a separation between the abstract properties of a data type and the concrete details of its representation. Got a good thing in here about Navajo code talkers. Now they talk about color representation. This is where you get your 255. So red would just be 25500, green 0, and blue 00255, because their color saturation is 255, but it's which one equals which one. Cyan, for instance, is kind of a turquoisey color. It's a mix between green and blue. So you can see, look through that. And when we're doing digital images, a lot of times using the ASCII code is better than just saying red or green or blue. Okay. How many bits will each color require when using the RGB encoding mechanism? Add that as your answer. Try to figure that out before you look at it. That'd be good. And then here it talks about the image representation. This is a common image from a bitmap. It can be regarded as a grid of pixels. Computer software saves information about each pixel in the image. So the data in the file that represents this image will include the RGB values for each pixel in the grid. And then they show you how to do it. And it says, for example, a monochrome black and white bitmap uses only 1 bit for each pixel. So if there's something in the block, it would be a 1. If it's empty, it's 0 for black and white. What would the file size be if the image was saved in a monochrome bitmap format? You can look that up. And now it says fill in the 12 by 12 downloadable table to create the monochrome picture represented in binary. Each pixel in the grid represents 1 bit of information. So go through and actually copy this and paste it into your notebook and fill it in. That would be great. And then the conclusion, without converting the numbers to decimal, sort the following binary numbers in descending order. So it wants it descending is highest to lowest. And then answer these questions. Create your own numbering system, choose a single digit, blah, blah, blah. Okay? You do not have to do the optional. You can if you want to. It's kind of fun. And again, there's my chart, my cheat sheet, so that I can go back and actually get its digital number. Okay? Okay, hopefully that will teach you enough about binary. You'll feel good about that. Save your Word document and upload it to Canvas. That's it for this video, and I will make another video on 113 and have it posted shortly. Have a good day.